Okay, so hello, and I'm Simon from HK Science and Technology Research Lab, which is in the western suburbs of Tokyo. And I'm going to be teaching this course on Introduction to Pattern Recognition. 2 lectures, and then you've got an examples class in the 3rd week. You may have seen those of you who've got the handouts. You might think there's a lot of slides, but there are quite a lot of slides, but I'm going to skip over quite a lot of the mathematical details. You can look at the printouts if you want. I'm also going to go fairly fast. So if there's anything you don't understand, you can ask me right there in the lecture, or after the lecture, or next week, or in 2 weeks from now at the examples class. So the outline of the course is, very briefly, I want to explore what patterns are, what does pattern mean, pattern recognition, what you trying to work around. And then the 3 main subject areas are feature extraction, pattern classification, and machine learning. I'm going to try to get nearly all the way through pattern classification today, because machine learning there are not so many slides as with these, but it's more dense. So I'm going to hopefully have most of next week on the machine learning stuff. It's also increasingly important relative to feature extraction in particular. So, straight in we go. So what are patterns? Well, they are regularities in data of some sort, as opposed to noise, which is irregular, randomness. The data can be discrete or continuous on an n-dimensional support. That means the independent variable, so the time axis, x and y space axes for images, x, y space and time for video, higher dimensions for other kinds of data. So here are some example patterns that you might wish to recognize. Here's a DNA sequence, which is a string of nucleotide bases with a 4 or 5 letter alphabet. Here's a seismogram, which is we had an earthquake alert go off in Tokyo in the middle of last night, night before, triggered by a seismogram somewhere in Chiba. Here's a 1D audio waveform. It could be a speech pattern that you would like to recognize, etc. So those are all one-dimensional. The independent variable is just one dimension. Here are some 2-dimensional patterns. Handwriting treated as images. Fingerprints, iris, and face. These are all very important for biometrics and authenticating whether people are who they say they are for security purposes. Here's another 2D signal. It's a little bit more specialized. This is a voice print spectrogram. We have frequency on one axis and time on the other. This is the back of somebody's hand, like that, where you're trying to actually recognize the pattern of blood vessels in the hand for authentication. These last 2 are 3D video examples. This is an example of activity detection in an airport, trying to spot whether people do anything anomalous, that's unusual behaviour. Putting a bag on the floor and walking away, for example. Also, recently there's been some work on gait, that's how people walk, because you can actually recognise quite a lot of people from the way that they walk. So, these are examples of the kind of things you might want to recognise. Application areas for pattern recognition are coding and recognition and retrieval of these various patterns, text or image or video. So, for example, image and video coding, which I'll say a bit about in a minute, for transmission, storage and search. Archive indexing For example, NHK, where I work, has a lot of TV footage in a big archive building up at Cowlitch, and they would like to be able to search this archive based on content. Right now, it's very poorly indexed. There are some indexes that someone has physically typed in, but if some event happens and you want to find the relevant news footage from that, from a related past time, someone has to wind through the video and find it. And it would be much nicer if you could use automatic recognition techniques to automatically create an index for the archive, so you could search it using text labels generated by the pattern recognition system. Data mining, duplicate detection. Speech recognition is another big one for TV subtitling, also for user interfaces and text entry. And I've left machine translation off there, which I shouldn't have left that off. That's another big one. Written text recognition for automatic mail sorting. OCR is optical character recognition. It's another big field. Medical screening and assisted diagnosis is another one, looking at particularly medical images and time series data from various medical instruments. Finally, biometrics and security, which it kind of overlaps with quite a lot of this. DNA testing and DNA sequence matching. Face and iris and fingerprint and signature and gait detection or recognition or verification for security, and abnormal activity detection, like that example in the airport. So these are the kind of things that people are doing. There are some more application areas I'll talk about a little later when we get onto the machine learning in particular. But first, let me say a few words about feature extraction. Going back into the history of signal processing, people have tended to use, as far as possible, linear features, which is features extracted from signals by linear operators of some sort. And an example of that is channel coding of images. So here are two images, one's artificial and one's natural. And there are several thousand pixels in each of these images, and usually we treat them as a single vector with all these pixel values stacked up in kind of raster scan order. So the thing about images is that when you're trying to code them, one of the things you're trying to do is reduce redundancy between pixels. So for example, here's pixel ij, that's row I and column j. And here is another pixel, just k pixels further along, so I, j plus k. And as you can see, or as you can imagine from this example, these two pixel values are probably either identical or very similar. In the natural image, the closer two pixels are together, the more likely they are to be closer statistically. So rather than coding and transmitting, if that's what we're trying to do, every single pixel value in this image, you could imagine several more efficient ways of doing it. For example, this pixel is white and the other 512 pixels in this row are also white. You could transmit something like that and save yourself having to transmit the same value 512 times. Similarly with the natural image, you could probably devise some kind of features that you could extract from the image which would tell you what you wanted to know more efficiently than listing all the pixel values. So, transmitting or storing on a hard disk all the pixel values is inefficient. For example, we will, hopefully by the Olympics, or in fact from the 1st of December this year, super high vision 8K broadcasting is going to happen. If you try to do that uncompressed super high vision 8K 60 hertz frame rate signal is about 48 gigabits per second, and you don't want to be transmitting or storing all that if you can help it. So coding aims to reduce the redundancy, but that doesn't tell you what features you should pull out and code from these images.
The way people have tended to pull out features from images in the past is still based on, even now, on convolution with linear filters. So here's a linear filter, H of I and J, or P and Q here. And here's the image F of IJ, and the output at some pixel IJ here. To compute that, we line up the filter mask here and the input image here, compute pairwise products between the pixel values and the mask values like this, add them all up, and there's your output. Then shift the whole mask across one pixel, repeat. Again, shift it, repeat, keep doing that, and you generate another image, effectively, GIJ, as the mask slides across the image. Now, most image and signal processing in one dimension has been based on these kind of linear features, but what kind of features should you extract with a system like that if you want to do, for example, coding of images? We usually use a matrix vector notation for this kind of stuff. So here's our image, all the pixels in a big one single vector, and that's going to be n-dimensional. Rn is an n-dimensional vector of real numbers. So in this image, the width times the height is going to be this number n, the dimensionality of the input signal. And then we're going to pass it through some linear transformation, which is represented by a matrix A. The T here is the transpose of that matrix for various reasons. We tend to use that. And that's going to give us an output feature vector Y, which is going to be m dimensions, so m real numbers. M could be less than or equal to n. It could sometimes be greater than n, but for coding efficiency, we'd normally be talking about less than n. Then at the end, after we've transmitted or stored and retrieved our signal, we do some kind of other linear transformation to reconstruct the signal vector sometimes, or we may just process these features as they stand. So we represent the data as this real-valued n-dimensional vector x. And here's x. We normally subtract the mean mu x here before doing anything with signals, just because, for example, if we're transmitting signals, there's no point transmitting the mean because it doesn't change. You can subtract it at the beginning, add it back in again at the end, and you get the same result without wasting bits transmitting it. So here's our transformation matrix. Output y, input x, subtract the mean, multiplied by the transformation matrix, and away we go. So if m equals n, that's to say if this transformation matrix is square, then generally if the transformation is invertible, and you can recover the signal without loss, should you wish to. If, on the other hand, we're extracting fewer features than there were dimensions in the input signal, then that's a non-invertible transformation, and it achieves literally dimensionality reduction, which can reduce the amount of data by extracting relevant features from the signal and from the noise, of course, so that we don't waste bits. So that's assuming that's what we want to do. All very well, but we still haven't decided what features we should use. Here's another slightly different example. Here's a face recognition system. Here's the real world. Here's a camera pointing at some bit of it in which this guy is. And we're going to extract some kind of features, maybe by a linear filter mask sliding over the image. And depending on the values of those features that we extract from this image, we're going to try and recognize this guy. So here we've got some feature vector, which was y in that last slide. And what we want to know is where that feature vector lands relative to features extracted from other faces in this database of people that we've registered up here. So we've got several examples. There may only be one, but ideally we've got several examples, each of person A and person B's feature vectors extracted from images maybe under different lighting conditions or different face poses or whatever. So here's the spread of person A's data in this feature space, and here's the spread of person B's data. And if our new feature vector, say it's two-dimensional, maybe we've got two features here, two linear filters that we've used to extract features from the image, then our feature vector from this guy's face is going to be somewhere in this feature space. And just looking at this artificial example, his data lands very close to many of the examples of person B and further away from most of these examples of person A. So we might decide that this is probably person B. Okay. There are many issues that I've skirted over here, but that's a simple way of doing it. And we would like to know what features are going to make this system work and what features would not make it work. So can you do anything statistically to get yourself good features in some sense? The answer is yes, you can. A classical statistical method is called principal components analysis. It has various other names, but this is probably the most common one. It's also called an eigenvector transform. So here we have our input vectors x in this space of real numbers, n-dimensional real numbers. We extract some m-dimensional feature vectors from each of these input vectors with our linear transform A again. This is exactly the same as the previous slides. Subtract the mean here from our input vector. This capital E here is expectation, statistical expectation or average. So this is the average of this our input data vectors. We're going to subtract that from each of our vectors, transform it, and generate a feature vector y. If we do that, then there are some things that you can say about the statistics of the signal y produced by this process related to the statistics of the input signal x and the transformation A. I don't know how many people are familiar with covariance matrix. How many people are familiar with covariance matrices? Yep, one or two perhaps, not very many of you, I guess. So it's unfortunate that the way the timetables worked out this year, you've got Matsui sensei's lectures after mine because I think she's doing the more basic statistical stuff, but couldn't be helped this year for timetabling reasons. Anyhow, so a covariance matrix briefly is an average value of this thing, which is an outer product of y with itself. What that says is it measures or expresses how much each element of this vector y varies with each other element of y, or covaries. So to go back a few slides, for example, how much this element of y varies with this element. If this element increases, does this element increase as well, usually, or does it decrease? Or does knowing this element tell you nothing at all about this element, for example? Okay, so that's what a covariance matrix is. And briefly, the covariance matrix of y turns out to be, if you substitute this formula for y into here, the transformation matrix appears at the front and the back, and this thing in the middle here is basically the covariance matrix of the input signal. Why is that interesting? It's interesting because if you choose your transformation matrix to be the the top, that's to say with the biggest energy, eigenvectors of the input signals correlation matrix CX, then you can show, I won't go through all this, but you can show then the covariance matrix of your output signal Y is diagonal. So there, it has these values on the leading diagonal, and it's 0 everywhere else. That means that the components of Y are uncorrelated with each other. Thus, this is a Kronecker delta, which is 1 when I and j are equal and 0 when they're not. So what that means, going back to that previous slide, is that knowing this signal here tells you nothing at all about any of the other elements of Y. And that's true for all the elements. Why is that a good thing? It means that you've removed all the redundancy. If knowing this signal told you something about, for example, this signal, then that's potential redundancy. If you encode both of them and transmit them, you're effectively encoding some of the information twice. So it's good from a coding perspective for all these to be uncorrelated with each other. Okay. In pictures, here's an input signal, two-dimensional. Here are the various example data, the data in our example set. And you can see that there's a general trend here that as x1 increases, x2 tends to increase as well, because the set is generally distributed along this kind of axis here. If you compute the eigenvectors of the correlation matrix of this data, the biggest one is this red vector A1 up here. The other one is this vector A2 here. They are perpendicular to each other. There in the middle is the mean of the input data, which we're going to take out, which effectively shifts this point to the origin. Okay. Another way of looking at this is that you can approximate your input vector as mean plus some kind of weighted sum of these eigenvector components. So in the case of the previous slide, we can approximate, let's say, this data vector here. We can approximate it as the mean plus a certain amount of A1 plus a certain amount of A2. And that's the most efficient way of expressing it if we're going to only encode, for example, A1. Okay. So, and if you do that, the coefficients of these numbers yi are from here, are the outputs of our transform. And another way of looking at it is that this reconstructed signal, if you will, is the orthogonal projection of the signal onto the subspace of these principal components. Don't worry too much about that. Here's an example of using this for face recognition. This was an actual face recognition system developed back in 1991. So you start with a set of training face images. Here they are. There are 15 in this example. They're aligned, so you need to try and get everyone's faces lined up. Usually they align the eyes, so you dilate and rotate and translate each face to get the eyes lined up with each other. So your data matrix, big X here, is then each of these images, X1 to XP, this one's X1 and that one's XP over there, stacked up into a matrix X. So then we're going to estimate the mean face, that's this here. You take a simple average of all these faces, that's what it looks like. And then compute the covariance matrix, take the first m principal components or eigenvectors of it, which span this m-dimensional subspace, so-called face space. And here are the eigenvectors, A1, A2, etc., etc. So if you think of trying to reconstitute a face, if I just go back to the previous slide, if you try to reconstitute a face as a mean plus something times eigenvector 1 plus something times eigenvector 2, etc., etc., you can think of a face as being this plus something times A1 here, which is going to make this area lighter and this area darker, plus something times A2, which is going to make this area darker and these bits lighter, and so on. And you can add more and more of each of these eigenvector images until you get as close as you like to the face that you're trying to reconstruct. And you can see that the larger eigenvectors tend to have larger features, and as you get further in here, there's more detail and less large black or white regions. So they express finer and finer and finer detail. So if you wanted, for example, to stop at the first, 6 eigenvectors, just transmit the coefficients for those, you could approximate the face, losing the detail that you would have got if you transmitted all these as well. So that's how that works. There is one problem with doing the naive approach that I just talked about, and that is that the covariance matrix of the data can be very large. In the case of 128 by 128 pixel images, this outer product here is this very large 16,000 squared matrix, and you don't want to be computing the eigenvectors of that. So you can do something called a keyhole trick, which involves, instead of computing the eigenvectors of this product, you can compute the eigenvectors of this product, which is much smaller. So anyway, don't worry about that. Here's a proof that it works. So projecting each of these faces onto face space. So now we've got, having designed our face space, now we have a bunch of faces that we want to register in our database. Now these don't have to be the same ones as we used to build the face space, but they often are. So here's a number of faces, RK, the kth face that we want to register in our database, and we project each of those onto our face space in the usual way. And then we can represent a new input face that we're trying to recognize by the same kind of thing. So form a vector of these coefficients by projecting the input face onto the face space, and then compare it, for example, by finding the nearest neighbor with the ones in the database. In pictures, it looks like this. So first we need to compute our face space, and the way that's, here are our images from which we're going to compute the face space. We do this keyhole trick thing, use the computation, keep the top m eigenvectors. In this case, I've just drawn it with all of them. And here's our face space with the mean, there's the mean face of these and all those eigenvectors hanging off it. So having computed that, that's what we're going to use to do the projection and feature extraction from all our registered and input faces. So now we've got a load of faces, RK here, that we want to register in our database. They might or might not be the same as the faces that we use to build the face space. Anyhow, what we're going to do is project each of those onto this face space, which means we're expressing each of these faces as something, or the mean plus something times this one, plus something times this one, plus something times this one, etc., etc. And those somethings, the weights, are how we represent each of those faces. So those are projection vectors from these registered faces. Then along comes a new input face that we want to recognize. We want to compare it to all of these. So subtract the mean, do the same thing again, project that onto this face space and get a bunch of weights, y dash here, and then we're going to compare that weight vector y dash to all these yk weight vectors that we got from projecting each of these registered faces onto the same face space. And we might find the closest one, for example, as we did in this case. If this could, for example, be the weights of the top two eigenvectors in the face space. Okay. All right, so that's eigenvectors and the eigenface method. People don't use eigenfaces very much these days, except as a teaching exercise for various reasons. One is that it's actually difficult to get those faces aligned properly. You can see, if I go back to here, you can see several different eyes, several different eyebrows, several mouths there. It's much better if you can to do a kind of non-linear warp to align the faces. So that's one of the problems with the eigenface method. There are others. So what are good features in general? Well, for classification, good features depend on what task you're doing, obviously, but they are robust, meaning that they should be similar within each class. So feature vectors extracted from the face of person A should all be as close to each other as possible, and they should also be invariant to input transformations. So if person A turns his or her head, or the lighting changes or whatever, you would like those feature vectors not to change very much. Ideally, you would like them to be completely invariant to these transformations. But they should also be discriminative, meaning that the feature vectors for person A's face data, various different samples of person A's face data, should be significantly different, if possible, from all the feature vectors from person B's face data, so that you can do the discrimination. So in pictures, something like this is going to be good. There's a simple boundary adequately separates all your data samples, and this is computationally pretty easy. This is less easy, but still not too awful. Here we've got a non-linearly separable pair of data sets, which again is not great. And this is bad, to say the least, where all the vectors are all mixed up with each other. So ideally we'd like to get as close as we can to this, and there are various ways of processing your data to approach this ideal situation. So talking about invariance and robustness, again using face recognition as an example, most errors in face recognition systems arise because of differences between the conditions under which someone was registered in the database and the conditions under which they appear, and you try to recognize them subsequently. So the system as a whole, ideally you want it to be robust to things like camera parameter variations. If you have a camera by the door of some building that's trying to recognize people to decide whether they're allowed in or not, ideally you want people's face pictures in the database to have been taken with the same camera at the same distance, under the same lighting conditions. Indoor and outdoor, particularly outdoor and sunlight, are nasty because they cast strong shadows across the face and disrupt your linear features if that's what you extract from your faces. Aging, people's faces change slowly. Makeup, deformations due to facial expressions and speech and so on. Hairstyle variations, wearing glasses or sunglasses or not, people with face masks on, hats, facial hair, and last but not least, 3D head pose, 3D meaning in this axis. Here's a fairly obvious example of the last one there. Here's two images in our database. If this is the input image and we just do a naive pixel to pixel match, This one's going to be the closest match, but as you can see, actually this woman is the correct answer. So we would like to do something more clever than just pixel to pixel matching. Well, like what? You might say, well, one thing is combinations of positional and luminance shape and texture features have been used. So for example, fitting a graph, an elastic net onto people's faces that moves with the face. If someone moves in 3 dimensions, the net moves with them and extracts features at hopefully the same locations each time. This was done, there's a thing called the elastic bunch graph matching system, which uses this. This system and variants of it are still used today. So 3D shape features are the most invariant to 3D head pose changes. Obviously, if you could extract a 3D description of people's faces, that would be lovely, but it's very computationally difficult. You need stereo cameras or shape from motion to get the 3D structure. In practice, for biometric verification, to authenticate people, features like the iris and fingerprint are actually more reliable, although they're more intrusive in general. Okay, this is the main textbook for this course, incidentally. Mainly because it's pretty much the only one out there. There are a couple of others. There's the Chris Bishop's book, which is also in the references, but that's a lot more mathematical. This is covers the basics much better. It is a bit old, but the basics haven't really changed until the last few years, which we'll come on to in the next lecture mainly. So here's an industrial vision task from this Duderhart and Stork is D8 DHS down here. And you're trying to categorize 2 types of fish on this conveyor belt. And the unrelated variation includes the lighting, the angle that the fish appears on the conveyor belt, and so on. So we're trying to decide whether a fish is a salmon or a sea bass. That's the task. Well, you could use, for example, the length of the fish. How does that work? Well, the black line here is a histogram of the lengths of salmon in your sample images, and the kind of pink, orangey pink line is the histogram of the lengths of sea bass. So on the whole, sea bass tend to be longer than salmon. If you put the boundary between the two at this length here, L star, that minimizes the amount of errors that you make. But because there's significant overlap between these 2 histograms, you're still going to make quite a lot of errors. So not very good. So, well, you could use lightness of the scales, because the sea bass has a lighter color than the salmon. So here's the histogram for the lightness of salmon scales, and here's the histogram for the lightness of sea bass scales. If you put the boundary there and you say everything lighter than that is a sea bass, everything darker than that is a salmon, then you're going to make fewer errors than you made on using length, but there's still some overlap. These sea bass and these salmon here are still going to get misclassified. So that's not ideal. Well, how about if you use both those features together? So along here now we've got lightness, and up here we've got length. For some reason in the textbook that changes to width all of a sudden. I don't know why, but anyway. So now we've got 2 features, and if we were only using one of them, we'd have either a vertical boundary or a horizontal boundary, but using both the features together, now we could put a diagonal boundary here that does better than either of those potential vertical boundaries. So with this linear decision boundary, we could say, well, anything that falls that side, we're going to call a sea bass. Anything that falls this side, we're going to call salmon. And by just rotating that whole space so that this axis becomes horizontal, that gives us effectively a single coordinate by which we could do this. So that is better. This is related to a technique called linear discriminant analysis, and this kind of formalizes what that's about. So we're going to try and find a single direction, v, this could be a unit vector, a single projection onto which best separates two classes. This is not the same as PCA, by the way, so don't confuse it with PCA. So here's a vector v through the origin, and we're going to project all our data of these two classes onto this vector here, and we want to find the direction of the vector that best separates these two projections. I think you can see from this example that these projections of the blue data points are much better separated from the green ones here than they are in this case where they're all mixed up. Mathematically speaking, what we're trying to maximize is the distance between the means of the projections relative to the scatter, or the variance of those projections. So we only consider second order statistics, which is correlations, and the thing we are going to try and maximize is this thing here, which is the ratio of, this is the projected mean of class number 1, and this is the projected mean of class number 2. So in this case, project all the data points onto this orange line, then the distance to the mean of the projections of class 1 is this thing here, mu1, and the distance to the other projected mean is mu2 here. The scatter is this thing on the bottom here, S1 squared plus S2 squared. That's the degree, the width, if you like, the spread of this data set and the spread of this data set. And you can see on the right-hand side here that the difference between these projected means relative to the sum of the scatters here is much larger, which is much better. I won't bother going through the mathematics, but essentially you end up with the separation of the projected class means being this thing here. V here is your unit vector that indicates where the line is that you're going to project onto. And this SB thing here is a scatter matrix, which is the outer product of the difference between the means, which is known as the between class scatter matrix. So that expresses how far apart the means of the classes are. There's another scatter, which is this thing, which again is this kind of quadratic product between including the vector that we're looking for, V, and another scatter matrix, SC, and that SC is this thing, which is called a within class scatter matrix for each class. And that is effectively just the covariance matrix of each class. So we just add those up, and it gives us this thing here. This is the within class scatter matrix. And it turns out that the thing we're trying to maximize is the ratio of these between and within class scatter matrices with, or the quadratic products of those with this vector V that we're searching. So we're trying to maximize this thing as we vary V by rotating it around the origin. Matrix calculus, we won't bother with all that, but it says we won't bother with all this. You end up with an eigenvalue problem, and this is the solution. So I'm just going to tell you what the solution is, and you don't need to know how to compute this. If you're interested, go ahead and read through that. So what's good about LDA? Well, it fixes the problem that a naively selected projection with which may separate the class means quite well, might not be the best given the scatter of each class. So here's an example in which you can see here that the separation on this axis of the class means is greater than on this axis. But because of the scatter of each of these classes, it actually means that the vertical axis here would be a better choice of axis to separate them because of the overlap horizontally between the two. It doesn't work in non-Gaussian cases or where the class information is actually in the scatter. So for example here, both classes have the same mean right in the middle there, and all the information about which class is which is in the scatter. So LDA won't work for that situation. Same goes for this one. The class means are both right in the middle, and only the scatter tells you which class is which. And in this case, the class means are fairly separated, but a linear separation of these classes isn't going to work. So I just want to say a little bit at this point about image features. What features do people actually typically use to extract from images for image recognition? As a caveat or not a warning, but this image features, people have spent their entire careers designing better and better image features. But now with the recent advent of machine learning and deep learning in particular, it's becoming less and less important. So if you were thinking, I quite fancy becoming an image feature designer, don't. But this is what people have used, and you should probably know about this because a lot of these features are still being used today, often in combination with machine learning techniques. So going back in the day, everything was linear. People used Fourier transform. I don't know if you're familiar with, probably not familiar with Fourier transform very much just yet, but effectively it's a frequency-based combination or description of signals. Linear edge detectors. Here's the output from an edge detector run on this image here. The so-called canny edge detector is the most famous one, and that is still used a lot today. If you look at the OpenCV open source computer vision package, you'll find all this stuff in it. And this is the kind of descriptor that you can extract with linear edge detectors, or they're linear in the first instance anyway. Gabor wavelets are another feature fairly commonly used. The elastic bunch graph matching system that I talked about a few slides ago, where you stick a net onto people's faces effectively, that used these features. The company that was the main producer of this lot got bought by Google, and so Google's face recognition uses these at some point. It uses these features are Gaussian windowed complex exponentials. In mathematical terms, it's this. This is a Gaussian window, which is like a big bell curve. This is a complex exponential, which is a sine and cosine. And for a couple of different values of the width parameter here, this is what one of these things looks like. So it's a windowed patch of a sine wave grating. And if you convolve these with an image like we did back in the second or third slide, at each pixel, what the output of this thing will tell you is how much of that frequency is present in the image at that location. So here's a bunch of them at all different orientations and sizes, and a bank of these. If you transform it into the frequency domain with a Fourier transform, which don't worry about that if you haven't done it, that gives you a coverage of the frequency domain that looks like this. A good thing about these is that you can estimate shifts between image patches. So if you're trying to match a face with a face in the database that is slightly shifted, then you can compute the shift with these features and correct for it. Okay, so these are used to align and deform templates for tracking and face recognition. Okay. Another feature very commonly used, and this is still very commonly used today, is these Haar-like wavelets, they're called. They're very simple features. In this case, subtract the average brightness of all the pixels in this top rectangle from the average brightness of all the pixels in the bottom rectangle, and you get a simple number. And as you can imagine, there are millions of possible placements of these pairs of rectangles on the image. So these measure difference in average luminance or brightness between adjacent rectangles in the image. Popularized by Viola and Jones. The OpenCV computer vision library, the main face detector in there, uses these features. It uses a vastly over-complete feature set, meaning there are more potential rectangular features like this than there are pixels in the image, and the classifier then learns which ones are good at detecting faces and which ones are not. So it uses a cascaded classifier with these features as the input, so that you can very quickly reject regions that are not faces. For example, if you compute this feature up here somewhere, it's not going to have the characteristic difference in brightness between the eye region and this region, and can very quickly tell you this is probably not a face before you go on and look at more complicated features. Okay, they can also be computed very, very quickly using a thing called an integral image. You compute the integral image once, and then 4 accesses to that image will give you the average brightness of any rectangle in the image. So they're very quick to compute. Okay, another feature used in face recognition and object recognition systems is a thing called local binary pattern. And that's a local feature which expresses which parts of some image neighborhood are lighter and darker than others. So, for example, at this pixel here, it probably might be a bit difficult to to see the numbers there, but the pixel brightness is 70 there, and what you do is you go round these neighboring pixels and figure out which ones are brighter and which ones are darker than the one in the middle. And if it looks like this, for example, where these 4 are all brighter than the one in the middle and these 4 are all darker, then that's a fairly good indication that there might be an edge running through that pixel in this direction. These features are invariant to monotonic transformations of luminance. So if the image brightness overall increases, it's going to make no difference to these features. They encode spatial light-dark relations in code words. Basically, don't worry about that. But these features are pretty good for face recognition. Histogram of oriented gradients, or HOG, is another. This tends to be used to detect people, whole body in images, particularly for automatic driving. Driverless cars use this kind of thing because obviously it's kind of useful to be able to detect people in images if you're relying on it to drive your car. So this feature expresses a distribution of gradient orientations within a region of an image. And this also is invariant to monotonic transformations of luminance, so it doesn't matter. The lighting won't affect these features unless you get something like a sharp shadow going across the area in question. but just increasing or decreasing the whole brightness doesn't affect it. You scan the image at multiple scales, suppress non-maximum, and away you go. Don't worry too much about the details, but here's an example. So essentially, here's somebody. Here are orientations measured with oriented filters at each several regions around this guy's body. The SVM here is a support vector machine, which we'll do when we get on to machine learning. But essentially, the support vector machine learns the statistical distribution of these things, these orientations, for the situation where there is and where there is not a person in the image. And this is the case where this is a positive. If you have orientations in these directions, in these positions, it's quite likely that there's a person there. Alternatively, if you have these kind of orientations in the same positions, then it's quite likely that you don't have a person there. So these HOG features have been used in this case to train this machine learning classifier, but we'll deal with support vector machines next time. Last feature worth mentioning is SIFT, scale invariant feature transform. This was really the main feature that people used, I would say, before deep learning came along, if they had big computers and a lot of time, and they didn't mind doing a lot of computation, because these features aim to take as much of the variation out of an image as they can by doing a Gaussian blur, do a blur, then take the difference of slightly differently blurred images, take extrema, maxima and minima of that, find key points. You can rotate the image then to line up all these key points and so forth. And you end up with a fairly complicated descriptor at each point in an image. I won't go into the details. You can look them up if you want. But here's an example of image matching using these descriptors. Here are 4 patches taken from slightly different viewpoints to this picture here. So, for example, this one here is the bottom of this totem pole here, taken from a slightly different vantage point. So there's a kind of distortion as well as the rotation. And the matching between those query images and the original gives you these quite good matches. So this is an example of using some fairly complicated features to make the subsequent matching more simple. Okay, so that's all I want to say about features. We will have a quick look at classification. I think we're probably going to get about halfway through classification. So this is the second main part of this course on classification, which is deciding, once you've got a feature vector or a pattern of some sort, deciding what class of pattern it belongs to. So the idea is to classify a novel input pattern according to the location in the feature space. That's this thing again. Depending on where this feature vector or pattern lands, decide which class it belongs to. Okay, and the way that's done implicitly uses decision boundaries, which are locations in your feature space which you decide where the classification changes. So in this case, it might be, for example, a line somewhere down here you might use in the most simple case to separate the A's from the B's. Or you might choose a slightly more complicated curved boundary if you don't mind doing a bit more computation, etc. So the decision boundaries that you're going to use are going to depend on statistical models of the input and the training data, the distribution of your data. and on performance criteria, how much computation you can do, how much memory it involves, how fast it needs to go, and the costs of getting it wrong. If you get the classification wrong, it may not give you a uniform cost. Cost of misclassifying an A as a B may not be the same as the cost of misclassifying B as A, for example. For example, if you let somebody into your building who isn't authorised to be there, that's probably better, or probably worse, sorry, than excluding somebody who should be in there, who can just phone security and get them to come and let him in. So, what kind of decision boundaries are there? Well, in decreasing order of complexity, exemplars, prototypes, and definitions, it's easier to use a picture for this. So here's exemplars, where we've got 3 types of example here, class A, class B over here, class C, and if we were using a nearest neighbour classifier, so-called, we would assign a novel input to the class of the nearest example, which in this case is going to be class A. Prototypes use a centroid rather than individual examples. So here's a centroid of these examples here is here, centroid of examples B is here, centroid of these examples is here, and we're going to classify this input according to whichever centroid is nearest. And in this case, it's going to be classified as B. Finally, we can define boundaries according to some kind of parametric model. Here's some lines, some boundaries that separate these classes. You'll see that all these A examples are up here. All the B examples fall over here. All the C examples fall down here. So all these lines, these 2 lines, separate these patterns correctly, but in this case, it's going to classify this input as C. So here we've classified it as A, here we've classified it as B, here we've classified it as C, same input. So clearly the choice of decision boundary makes potentially a lot of difference. The best you can do is a thing called the Bayes classification. The way that works is we assign a feature vector to one of big C classes, I from 1 to C. Classes are called omega I, and for each class we define a discriminant function, this GI, which is a function of the input vector X, and you assign class X, you assign input vector X to whichever class has the biggest discriminant function at X. So for all I not equal to M, all the discriminant functions for class I are smaller than the discriminant function for class M at the location of your input vector. I think the battery's dying on this pointer, so I'm going to switch over to red now. So for minimum error classification, if you set these discriminant functions to be this thing, which is the posterior probability that the given value of X came from class I, then that will give you, you can show that will give you the minimum possible classification error. And this follows from a thing called the Bayes decision rule, which is essentially what we just had on the previous slide. So this is, if, I don't know if you're familiar, I should just check, are you familiar with conditional probabilities? That this thing here is a conditional probability, and it's read as probability of omega m given X. So the probability that X came from the mth class given the value of X. So the Bayes decision rule is that if the probability of a particular, the mth class is bigger than the probability of all the other classes for a particular X, then assign x to that class, which may sound kind of obvious, but you can show that that minimizes the average error rate, which is then called the Bayes rate, P star. Don't worry about this, it's just showing that that's the case. Although that choice of discriminant function will give you, and you can show that it will give you the minimum error, it's not the only discriminant function that will give you the minimum error. Some others may achieve the same minimum error. There's a thing called Bayes' rule, which expresses a conditional probability this way round, probability of omega given x, in terms of the reverse, probability of x given omega. And this is that so-called Bayes' rule. Don't worry about it if you haven't covered it yet. Take it from me that this is true. We're not worried about the probability of the input vector itself, because that doesn't depend on the class. So we could, instead of setting the discriminant function gi of x to this thing, we could instead set it to the top of this fraction, which is this. And that will produce the same ranking of the classes, because this probability of the data is the same for all classes, so that disappears. So this will give you the same ranking. It's maximum for the same mth class as setting it to the posterior probability. We can also take the log of this, since log is a monotonic function. It doesn't go like this. It's a monotonic function. So you can take the log and still the order won't change. So we can take the log of this product up here, which is log of this thing plus the log of this thing here. Now this thing is the prior probability of each class. That's to say how likely your data is to have come from each of those classes before you even know what the data is. So if some classes are just more likely than others in the data. And this thing here is a thing called the log likelihood. This probability here, probability of x given omega I, is called the likelihood of x, given that it's from that class. So that tends to be the function that's used. Decision regions in feature space are regions within which one of the discriminant functions is maximum. So the boundaries are the edges of that space. So that's just saying the same thing again. Feature vectors get assigned to the corresponding class for which the discriminant function is maximum. So here's an example projected onto, these are intended to represent the probability distributions, the likelihoods, or actually the posterior distributions of class 1 and class 2 here for two-dimensional data. Data is somewhere on this two-dimensional support. And if you project this all down onto this bottom plane here, here's a decision boundary here, which runs kind of between these two peaks here. So if your input vector is in this region here, you're going to assign it to class 1. If it's over here, you're going to assign it to class 2. Also, if it's over here, you're going to assign it to class 2. Because if you do the math, you may see that the height of this peak is not as big as the height of this peak, and actually it's more likely that an input over here has come from this distribution than from this one. Now, at this point, I used to have about 10 slides showing the shape of various decision boundaries for different types of Gaussian variables, but I decided that you probably don't need to know that. If you do need to know it, you can go and look it up in the book. I've just replaced that with this one slide, which goes through the log form of that discriminant function this is the same as the 2 slides ago. A common model for the data in each class, including apparently these. You can perhaps tell these look like bell curves, they look like Gaussians. A common model is multivariate normal or Gaussian distribution with this mean mu I, and the covariance matrix is written as sigma I. It's unfortunate that people use sigma as a notation for a covariance matrix as well as for a sum, but you'll see that quite frequently. And this is a Gaussian density, Gaussian probability density, which looks like a bell curve in d dimensions here. So this is a constant, and this is a quadratic form, including the mean and the inverse of the covariance matrix. And that's what the probability of x looks like, assuming that it comes from the ith density and the ith class. And each class will have one of these densities. So in this case, here's the density for class 2, here's the density for class 1. Each class will have one of these, and if that's the case, then taking this form, the log of the likelihood plus log of the prior probability, gives you a discriminant function that looks like this. This quadratic product here comes straight from here. The log here gets rid of the exponential there. Those cancel out. This constant comes from here. And this is the same for all classes, so you can forget about that when you're trying to decide which class your data's come from. And this is the covariance matrix for the ith class. Again, if that's the same for all classes and they just have different means, for example, then that will disappear. And this finally is the log of the prior probability expressing the increased probability of some classes over others. So the boundaries can be simple hyperplanes. If all your class covariances are the same and they're all symmetrical, then the boundaries are simple, straight hyperplanes, or they can be more complex, depending on the shapes. So that's all I'm going to say about decision boundaries, apart from to mention that stuff tends to be used when you have a reasonable Gaussian model of each of your classes of data. When you don't have a reasonable parametric model of your data, what tends to be used is some version of a nearest neighbor classifier. So here's a nearest neighbor classifier, and what it does, like it sounds like, is it classifies a novel input feature vector according to the class of the nearest training vector, your data sample, effectively. So again, this is from the Duda, Hart and Stork book. So this is a so-called one nearest neighbor classifier in a 2D feature space, 2 classes, red and black, I guess that is. So the decision regions, which is all of these polygons here, they form a so-called Voronoi tessellation of the feature space. So if an input lands here, for example, it's going to get classified as the red class. If it lands here, for example, it's going to get classified as the black class. And this pattern of polygons is a Voronoi tessellation where each of these lines crosses midway between each pair of neighboring data points. You can show that with enough training data, the decision boundaries can be arbitrarily complex with arbitrarily many classes. It's not you can show, it's just they can. In principle, it's unnecessary to model the class distributions if you have enough data. You can just throw as much data as you've got at this problem. You can show that with unlimited training data, the average error of a nearest neighbor classifier is less than double the minimum error that we saw in the previous section, P star. And that was proved back in 67, so that's 50-year-old result, 51. Well, that's not bad, but there are conditions for that to be true, including you've got to have enough training data to cover the input space, and the input space is d-dimensional, and as d increases, you encounter something called the curse of dimensionality, which means that it's much harder to cover spaces of increasing dimension. And the training data, obviously, perhaps, must statistically represent the input data well enough. The computation and memory aspects of this in a d-dimensional space with n training vectors, here they are, here's your training vectors in a d-dimensional space. For each input vector, we need to compute, in principle, we need to compute the distance to every one of these training vectors, and so we can find the smallest. So that's a d-dimensional sum over an n-dimensional product. We have to repeat this n times, find the minimum. So this computation increases on the order of d times n. So d is the dimensionality of your space, and n is the number of training samples you have. So that could, if d and n are both large, this could be bad news. There are some things you can do to improve this performance. You can classify a novel input feature vector according to a majority vote. Instead of just finding the nearest input sample, you can say, well, we'll take the k nearest training vectors. For example, this is the nearest 5 vectors to this data point, and take a majority vote among them. And the class which has the most vectors within that neighborhood wins the contest. That may be better, may be less noisy than using a one single nearest neighbor classifier. It reduces the effect of outliers, that's non-typical training data, because in effect you're doing a kind of averaging. The average error rate, you can show further approaches the Bayes rate. The single nearest neighbor classifier can achieve twice the Bayes rate. Average error rate can further approach the minimum, the Bayes rate, if you have unlimited training data. And you're prepared to take quite a large number of samples. So in practice, you get a trade-off between computation and accuracy. These are the conditions. So as the amount of training data that you have gets arbitrarily large, and the number of vectors you include in your majority vote also gets arbitrarily large, but the ratio of the two is small, tends to 0, you can show that the k nearest neighbor classifier error rate approaches the Bayesian error rate. Don't worry about this graph particularly, but it shows how the error approaches the Bayes rate as you take increasing numbers of samples in your majority vote. So what can you do to reduce the potentially large amount of computation? There are 3 main things you can do. One is only to perform partial computations of the distance from your input vector to every one of your training vectors. So here, back from the other slide, this is the same equation again. You could, for example, instead of using the whole d dimensions in this sum here, you could use only a subspace of lower dimension for this sum. For example, when we spoke about principal components analysis, you could, for example, just use the onto the m largest dimensions. You could use an m-dimensional subspace, and you could abort this sum as soon as it exceeds the current minimum distance, because you know then that your input vector is not going to be the nearest to your to this particular datum, training data. Another thing you can do is you can pre-index the training samples. So you can use a tree like this to partition the feature space and only compute the distances to training samples which lie in some part of the feature space. So let's say here's your input vector, this blue cross. Because it falls in this quadrant of the input space, we'll say, well, we're only going to compare distances between the input vector and these vectors which fall in that space. So that's going to reduce the amount of computation you have to do. Obviously, however, you can miss the actual correct result. So this will increase the error at the cost, it will increase the speed at the cost of also increasing the average error. Another thing you can do, last one, is edit the data set. You can remove samples that are surrounded by neighbours that have the same class because they make no difference. Another thing you can do is remove samples near the boundary which you consider to be noise for some reason. So here's some examples of that. Here's some examples for seven vectors included in the majority vote, 7 nearest neighbour classifier. If you remove samples of different class from the majority of their 7 nearest neighbours, you can then use a simple 1 nearest neighbour classifier to get the same result. So, for example, from this data set, you can simplify it by getting rid of these samples. For this data set, you might decide that these look like noise and you're going to ignore them and put the boundary there, for example. Okay, I won't go into those with much detail. Okay. Right, this would, I think, bear in mind that it's now just after 6, this would probably be a good point to leave it for this week before we get on to overfitting and generalisation. So, does anyone have any questions on this week's stuff up to this point? If you think of a question afterwards, by the way, you can always ask me next week, or you can get my email address and mail me. So. We didn't get quite as far as I was hoping to get this week, so maybe next week will go on a bit later than 6 o'clock. Okay, well, if there are no questions, then thanks for coming today, and see you next week. If there are any questions, feel free.